very happy to be able to present this little knowledge sharing session. So this is part of my celebrations of having released my book. I spent 2 years researching and writing it, so I'm very happy that this is finally out. And today we're going to see a little bit of the philosophy of feature engineering that I put forward, and then some examples on things that I hope can be useful for you. The type of techniques we're going to see are relatively simple. There is possibilities of exploring the more complicated aspects of it, but that will be left for you to explore with this data. Okay, so we are now at half the people. So as mentioned, then we have 2 parts. The first part, we're going to go through this slide. I'm going to go through these slides, and I'll be monitoring the chat if I can see it here. Yeah. So in the chat, I have posted the links to this second. So I'll link to the slides in case the video is not clear, and also a link to the notebooks we will be using. So these notebooks open fine on Google Cloud, so you can open them and run them if that takes a while to load. And there's a link to the source code and the data from the book I wrote. And feel free to ask me questions on the chat. I don't know how you handle the, I see everybody's muted, so I think that's done on your backend. But you can hear me well, I assume. All right. I hope you can hear me well. And so what we're going to see is the feature engineering cycles, the importance of domain knowledge, and mention a little bit about how to combine features, how to reduce features, and how to handle variable length raw data. This is feature engineering on traditional machine learning systems, so we won't be talking about deep learning at all in this workshop. They shared with me the list of interests of 1 or 2 people that signed up that were interested in feature engineering and deep learning. Well, of course, very interested in that topic myself too, but we are not yet at a point to be able to share a full vision of the topic. Is still too early to being able to intertwine them properly. Then we're going to see this little example on temporal data and on spatial data. So we're going to start with spatial data. And spatial data, we're going to talk, particularly we're going to see the techniques of using radial distance to landmarks. And we're going to be using data from the trajectories of Nigerian cuckoos, which is very simple. This is type of data that is easy to share, but is representative of using trajectories in general. And then we're going to see a little bit of work on time series. I think that's going to be relevant to some of the people that sign up that says that how you handle a lot of small time series. Okay, so it looks like we are almost everybody, and we can now start. And thanks again for joining. I wish I have managed to make it to Nepal to meet you in person before the pandemic hit. Now, you never know when that will happen, but I have been involved with Fusemachines for more than a year now, and I really enjoy working with you all. So, what is feature engineering? from my perspective, feature engineering is the process of representing a problem domain as to make it amenable for learning techniques. So it's a process that involves initial discovery of features and their stepwise improvement. And it's based on domain knowledge and the observed performance of a given machine learning algorithm over a specific training data. And another way of thinking of feature engineering is trading amount of data with human time. Yes, in computer science, many times we can do things like trading time with space. Yeah, we can speed things up by using a cache that uses more RAM, or you can use less RAM by doing multiple passes on the data, which take more time. In a similar perspective, you can imagine that feature engineering dispense the need for large amount of data by tackling into available expertise. Yeah, so we are adding human knowledge that helps solving problems using computers. Overall, the field has moved away from feature engineering as a way of building artificial general intelligence. Yes, because it doesn't not help building autonomous intelligence systems, but it definitely helps solve problems. And many of the problems tackled by Fusemachines engineers fall into the categories of things that will take advantage of feature engineering. So I did my PhD back in New York. Actually, it was the same time with Samir Maski, and my thesis was on weekly supervised learning for text generation. Was part of the deep QA system that built the Jeopardy show, and in particularly, I helped build the last feature merging and the feature engineering component of the system. And that's where my interest on the topic really started. This here is a diagram of the 4 stages cascading logistic regression systems we have at in the show. And so in a way, we build a deep learning system by hand. Yeah. All right, so the feature engineering cycle I propose is a cycle that contains the normal training a model and testing on held out data within the whole cycle. But if you use a good split of train and test, or use cross validation, you know the model you are training is not overfit. Yeah. But when you do extensive feature engineering, you risk overfitting your features, yes? So you may find that certain features are very informative, but for example, you were using data that was collected during the summer and won't help during the winter, or things like that. So for that, I propose to take the raw data that before you are going to do featurization. I'm sorry? All right. So, so I propose to take that raw data, split it to have a held out to try the featurizer at the end of the process. So in this process, you will be iterating, doing exploratory data analysis and doing error analysis, coming up with features, and then evaluating at the end whether these features you have come up with have not overfit the raw data you use. Yeah, and the thing is that feature engineering can overfit much more than regular machine learning models. So it really has to be handled with care. So I assume, well, from the engineers I have worked from Fusemachines, I understand you're very familiar with exploratory data analysis, this idea of summarizing the characteristics of the data, normally through visual means, and formulating hypotheses. In the case of feature engineering, the EDA helped us come up with this initial featurization. And in general, EDA helps pick the machine learning model. Featurization and feature engineering is very tied to the machine learning model you are going to be using. Certain machine learning models require normalization, for example, or scaling, or can handle a lot of features, while others need very few that are very informative, etc. I advocate for feature engineering a human-in-the-loop process, where after each iteration, time is spent trying to understand why the feature, why the system is failing. Yes, and the idea there is try to zoom in into different types of errors that the system is making and formulating hypotheses, testing those hypotheses back, and coming up with revised features. Yeah, and again, even though you use certain examples to do the error analysis, you have to make sure that these hypotheses cover a lot of errors. Yes, otherwise you will be over-optimizing and over-engineering. So what makes for good features? What is that we're looking for here? Good features are informative, so describes something that makes sense to a human. That's quite important these days for explainable AI. They're useful, so the feature is defined for as many instances as possible, and is discriminant, so divide instances correlated to the target class. When we talk about feature engineering, right now there are some pretty good libraries to do AutoML that handles many cases of feature engineering by themselves. Yet, in general, you should try the AutoML before doing feature engineering by hand. If your problem gets solved by AutoML, then you don't need to go through the time-consuming process of doing a feature engineering by hand. But because the search space of feature engineering is so large, it's quite hard to get it right. A technique that is very useful for doing feature engineering is what is called feature drill down. When you identify poor features and try to drop them, and you find good features and try to make small changes to improve, to generate other features that you can put alongside the original one or replace them to see whether it helps. Okay, so besides doing this type of feature drill downs individually, other things we can do with the features is to combine them. Yes, and in a way, we look at the whole features and we look at them together. Why? Because one way of improving the quality of the features is to give them more context, to give them more meaning. So that's the idea of normalizing them, for example, of discretizing. A key concept in feature engineering is this idea of nuisance variations. You have the same information and it has changes, and those changes are not meaningful to the problem at hand. So we're going to remove those nuisance variations, for example, by normalizing the features or by discretizing them. And so then we take the whole data set, we compute some statistics like the mean, and use them to scale and transform the feature set. For this type of things, something that is quite useful is the idea of using histograms. Yes, and that way we can take a large number of not particularly informative features full of nuisance variations and transform them into a smaller number of features that is the count per each beam. Yes, and this is very popular in pre-deep learning image processing, and this is a technique that you may still want to consider if you are doing machine learning over sensor data, where you cannot use some pre-trained deep learning models. Another issue is that histograms in text processing are very popular, but they go by the name of bag of words. But a bag of words is just actually an histogram. And histograms are a type of descriptive feature. So these are features that instead of being the actual feature are describing how the rest of the feature set looks like. And you have things like the maximum, the minimum, the average. One of the very useful things about the descriptive features is that they are always defined. As you most probably familiar in real life data sets, there are plenty of missing elements on the data set. So the descriptive features are features that are more robust and more reliable. A common example is that the length of a piece of text sometimes is much better predictor than looking at the actual words. Yes, for example, if you want to see if a customer is happy or unhappy, a longer review most probably indicates that the customer is unhappy. The other thing you can do is you can expand features. Yes. For that, you look into what's called computable features. there are certain things. For example, deep learning models have a very hard time approximating ratios. Yes, so if you suspect that a ratio is useful for solving the problem, a ratio between two features, you can provide an extra feature by computing that ratio beforehand. So these are small, these things are called computable features and small programs that encode domain knowledge about the problem and the data set. Another common example is body mass index that you take is computed from the height and the weight and give you an idea about the overall health of the person. Other type of expansions includes imputation, when you have missing features and you have to come up with a value for them, and smoothing, when you consider that there may be errors and you are trying to approximate and reduce the errors by taking an interpolation of the values. Handling missing data, as I was saying, is very, very common problem with real-life data sets. If you don't actively solve the problem, you may end up having with a default, which in many machine learning toolkits is a 0, and most likely is not what you want as a default. Yes, the default you want for imputation, the default you want for missing data is a number that it will be as inconspicuous as possible, that will not attract the attention of the machine learning. Yes, it's a number that will make the machine learning look elsewhere. Yes, so an average will be good, for example. And the other aspect is if you have a feature that will be imputed quite a bit, you also want to add an extra feature that this is a flag saying this feature has been imputed, because the fact that the feature is missing sometimes is very informative, and you want to keep it aside. And this is what is called the missing data indicator feature. Yeah. Another issue with imputation, I mean, the best way of handling imputation is use nearest neighbor and train a separate classifier that says, well, given this instance, other similar instances that have this feature defined, this is the value they have for this feature. But that may be too complex in the general case. And I have some examples of this program in some of the Jupyter notebooks that I released together with my textbook. The most common feature engineering technique, the one that everybody associates with feature engineering, is feature reduction. Yeah, that's feature reduction, either by dropping features in feature selection or by doing a dimensionality reduction to a smaller space. So feature selection is one of the most common approaches in machine learning, particularly because many times we start with very noisy data. We use the whole raw data as a feature vector. So there are many columns that are unrelated to the target, and we want to drop them. Yes. And also because larger number of feature vectors means more parameters, means that you need more data. I won't be talking much about feature selection. It's normally a staple of machine learning courses. Many algorithms, though, don't need to have explicitly done the feature selection. They do it inside the algorithm itself through a process. They call it embedded feature selection, which in many cases end up being a regularization process, which is a situation where we tell the machine learning algorithm, okay, these are all the models you can build to express this data, but I'm going to add this extra constraint that you have to find the model that is smaller given this metric. And regularization is very popular with neural network, for example, or logistic regression in general. If you don't regularize it, it doesn't learn well. And there are different penalties that you can do to say how big has to be this parameter space, how is defined the size. Yes, you can define the size as a linear combination or as a square of the number of parameters and yeah, techniques like that. The other thing that is very, very popular when we think of feature engineering is dimensionality reduction. In dimensionality reduction, we take the feature vector and we compress it to a smaller dimension using different identities. Something that I like to try many times because it's very fast to approach is to use the hashing technique. Yes, so you just take, you basically do you map each feature vector to a smaller space just using a one-way function. And this is quite incredible that it works at all. A little better technique is to use a random projection. Yes, and this is an actual projection, so things that are nearby will end up nearby. The one who is very, very popular is PCA, or singular value decomposition, where we compute some idea of the direction of the data set and we project in that direction. Even though people like to give it a big emphasis to PCA, the direction of the data set is just a mathematical identity. That direction doesn't mean it will be useful in the domain. Yes, so I like to take PCA with a little bit of a grain of salt. Another technique is to cluster the data and use the number of the cluster as the feature itself. Yes, and finally you have these techniques in deep learning for computing embeddings, like word2vec or so all these techniques achieve dimensionality reduction. And so the last topic on the theory part we will discuss a little bit is how to handle variable length feature vectors. If you are not, if you are using deep learning, you know how to do this. You just use a recurrent neural network, or you use convolutional neural networks, and those things work fairly well for variable length feature vectors. Now, if for the amount of data you have, or for other constraints for the project, you want to use statistical machine learning, not deep learning, and your raw data is variable in length, well, then you have a problem because those other techniques really require a fixed length feature vector. So I will discuss very briefly some techniques to encode lists, sets, and trees. So sets are the simpler case, yes. You have multiple elements without ordering, but you know beforehand which are those elements. So then one way you can represent this is by using a list of indicator features. Yeah. So you transform this set into, let's say you can have 10 elements, 10 indicator features that says whether that particular element is in the set or not. Yeah. But of course, this doesn't work if you have a set of floating point numbers. Another technique is to use a machine learning model that can accommodate associative operations such as additions and multiplications. This is a common way to represent a set of word embeddings. You add the vectors, yes? And finally, you can sort the set and encode it as a list. And then we get into the next technique. So lists have two problems, yes? The exact positions on the list is a very important source of nuisance variations. And the second one is that the list itself has variable length. One technique to handle the variable length is just to take a fixed length that is long enough and pad the shorter list with a null value. Yes, and this works if the position has an exact meaning, but for language it gets very complex because, for example, if you say cancel my account versus please, I would like to cancel my account, the word cancel appears as feature 1 in the shorter version, but it appears much down the feature vector in the other version. But for example, you can say, well, I identify that please, I would like you to is not important, so I drop it, and then you end up having the two. Other techniques involve using a fixed region histogram. Yes, so you say, I know these words or these elements appear at the beginning of the list versus this appears at the middle versus this appears at the end. By far, the most popular way of encoding lists is to use n-grams, pairs of words or little windows of words of features that appear over the list. And these ones maintain the local ordering, but don't talk about the global ordering. You can do something like this together with a fixed region histogram to then obtain some idea about local orderings and global behavior. And finally, we have trees. Trees is a little more complicated because, well, you have a parent-node relationship. You can linearize the tree, yes, going from the first traversal and code it as a list, or you can use the tree equivalent of n-grams that are parent-node pairs. So if you have this little tree here, I eat the burger with mayo, then you can encode that as these pairs there, and the parent node eat burger is highlighted in the tree. Okay, so now this is what I have on the general feature engineering topic. Let's talk a little bit about spatial data. So spatial data is complicated by the fact that you are dealing with coordinate systems, yes? And because we live on a planet that is a sphere, then the distance are not lines, but arcs. And even more so, Earth is not a perfect sphere. Its rotation has resulted in a slight bulging on the equator. And latitude and longitude are not comparable as you move further north. Latitude shrinks, yes? So at the equator, 1 unit of latitude and 1 of longitude represent more or less the same distance, but as you go further north or further south on the planet, the latitude shrinks. And the other issue is when your data crosses the anti-meridian, that will be the meridian that goes all the way back from London, yes, the longitude goes from minus 180 to 180. So if you take average around that region, nothing will work. So these are the things to keep in mind when working with coordinate systems. So the technique I want to share with you today is radial distance to landmarks. And again, the whole concept in feature engineering is this idea of injecting human knowledge to make the data have a richer context so it's more informative to the machine learning. So you have points in a map, yes, but what we know is that these points are not necessarily that different. What you want to know, there are certain positions in the map, these landmarks, and how far away you are from the landmark is much more meaningful than the small variations between one little GPS location and the other. Yes. Moreover, that distance, you can take even a radial distance. It doesn't really matter whether you're further north or further south. Yeah. And so then each distance to each landmark becomes a new feature. You go from having 2 features, the GPS location, to, if you have 10 landmarks, 10 features, 1 per landmark. And it's just the distance to it. Another technique that I would like to mention to you, but we are not going to see it, is a particular type of spatial interpolation called ordinary kriging that allows you to have a feature, to have a certain information available for specific points in the map, and then calculate the value of that function on other points. Yes. So in the example we are going to see, we know the elevation of different cities. We can assume a smooth movement of elevation, and that way we could find the elevation of any point in the map, particularly the points for which we have a GPS location. So that's the type of things for which kriging is very useful. And kriging is related to a particular type of graphing we do in spatial data called a baryogram that shows how much difference in space relate to difference in the target data. Yeah, so it gives you a cloud of points that represent the variability of association between distances to target data. In a way, it gives you an idea whether the kriging will be useful or not for the data you have at hand. Now, for temporal data, there are two big sources of temporal data. One is time-stamped features, so historical data. You have a certain target function, and you have features for that target function from the past. And the second one is time-stamped target, with a time series. You're trying to predict something that is changing over time. And you are using the past values, plus maybe other features, to predict that next value. I do have a whole example of historical data on the book, and then there is a notebook there, but that takes a very long time to run, and it's very complicated. So in this workshop, we're just going to look at the time series example. There are many things you can do with historical data. So far, the most useful I have seen is just to use that extra data augmentation. So if you want to predict something this year and you have data from 2015, maybe a joint expanding the feature vector with this information will give you a more informed classifier. So that gives you the idea of lagged features. Yes, you have the value of a feature today, and then you have a value of the feature 3 years ago, a t-3. Yes, so it's a lag 3 feature. And many times you don't actually want the value, but you want to have an idea of how much the feature is changing over time, some idea of the velocity of the data. And so you can add delta features, and you can compute the difference or the ratio from the current value. And historical data in general, you really have a big problem with imputation. It is rare that you have all the features you have this year defined for the previous years, because features normally come from an acquisition pipeline, and those pipelines get expanded. So many times data you need is just not available. Then for a time series, yes, it's a topic that is studied more in statistics than in machine learning, and it comes from this. It predates computers. People were doing time series for astronomical processes 200, 300 years ago, and so these are the models themselves are simple, but the theory is vast and complex. In general, what you have is you decompose the time series into 4 components: the trend, the cycle, the seasonal, and the irregular component. You try to remove the trend, and then use the techniques to predict what remains. Yeah, and there are some models that are very popular for that. The autoregressive process AR model that captures some sort of organic growth. One way of thinking is that Fibonacci is an R2 process. Yeah. So it depends on a history of the 2 previous values. And those numbers are the numbers that for feature engineering we want to get. There are statistical tests that will try to, that will give you, if this time series is an autoregressive process, what are its parameters. You also have a moving average process, and ARMA that is a combination between the 2. Yes. So the moving average is expressed by a Q parameter that also gives you the size of the window. And then the AIR is expressed by the P, and then these P and Qs can be used as features for machine learning. But by far the simplest thing you can do if you're trying to use machine learning to deal with a time series is to train using the previous values of the target data as the features, yeah? All these Markov features. And depending how many previous values you take, that's the order that you are looking into. Okay, so this is what I have for theory, and we will now look into the code. So to reiterate, feature engineering is a way of adding human knowledge as intuitions to a machine learning solution. Many times as technical experts, we forget they are domain experts. Yes, so that human knowledge can come from us studying the data, but can also come up from the person who is asking for our help. We can ask them their intuitions about the data, which things they believe are useful for this problem, and that can open up a lot of untold potential. And again, for feature engineering, there is a number of well-understood methods. To me, the process is better done iteratively, starting from exploratory data analysis and doing error analysis after each iteration. Spatial and temporal data has plenty of human knowledge and intuitions that can be used for building more informed systems. So if you want to learn more from feature engineering, there are a few books that have come up recently. I will talk. So the first one is the first half is like bootcamp. The second one is a particular theory that the author pushed. The third, the CRC one, the 2018. This one is that one has a lot of time-related content, and it's a collection of papers. And there is another one that came up this year that is a cookbook in Python. My book is really focused on helping practitioners, people who are already familiar with machine learning algorithms. So it's less intended for teaching in particular boot camps or people who are learning machine learning. And I went through about 300 different, it cited 300 sources. So I kind of put together information from books, blogs, papers into a consistent format. And the nice thing is that half the book are case studies, which are available open source in the website. All right, so let's now take a look at any questions. You can just post them on the chat. So now,
I have a question about time series data.
Yes. Who am I talking with?
I'm Isu.
Okay. Nice to meet you.
On my screen. Hi. So I was wondering, like, for example, we're trying to predict sales, right? And we have data, historical data, and we're predicting sales for this December. But what we didn't know before is that there's a global pandemic, right? So that data is not included in that. But now we do, and we know that's going to affect it in a significant way. So is that how?
That's called that's called a black swan event. So in those cases, the historical data is not useful.
Yeah.
The most you can try to do is some. If you can do some causal modeling and try to do some counterfactuals there, but so those things are the killer for time series. The most I have seen is people who say, well, you cannot predict the subprime mortgage crisis, but there was a crisis like that in the 90s in Japan. So you can use the Tokyo data, and that Tokyo data will help you have better models during the subprime crisis. Yeah.
I see.
So in this case, you will have to try to find another place that suffer maybe a more localized pandemic to do that.
I see. Actually, like to kind of clarify my question, what I was trying to say is that is there like any kind of feature engineering where we also include as a feature, like the real time predictions of humans, like projections of humans, and that is also taken into account as a feature,
Yeah. So if you manage to make it to a temporal time series, so that the beauty of using machine learning for doing time series is that you can add features. Yeah.
Right.
And here we will see predicting the population of a country using the number of Wikipedia links that the web page, the Wikipedia page for the country has. it's a completely arbitrary feature, but it helps predict the population of a country. Yeah. So when you use machine learning, then you can throw them a lot of features. If you want to use features with statistics, time series systems, it becomes very difficult. But let's start with the spatial landmarks that is much shorter and easier. So this one I post on the chat, the notebooks, they're on GitHub. You just come here and you press the opening collab, and you will get it here. The collab clones the notebook to get the data, yeah. And the data we'll be using is these trajectories of satellite telemetry for 6 African cuckoos in Nigeria. Yeah, so they went from Nigeria to Cameroon. And the data comes in CSV format, and it has a number of columns. We will be using just the location, latitude, and longitude, and the individual. And we are splitting the individual in a, so we train in some individuals and some birds, and then we test in other birds. And the problem we are trying to predict is whether the animal will be moving in the next hour, I think. So using volume, we can see the points. Yeah, so these are the points. We can see here that there are certain places where the birds seem to have spent a lot of time, and other places where they just were flying around. Yep. So, so the first visualization, we try to split, open up the time, the moment when the animal was, and the assumption here is, well, maybe at night most probably they were not flying, and during the day they maybe have been flying, or vice versa, depending on how the animal behaves. So that the moment the animal, the moment the data happens is quite important. So we have the year, the month, the day of the year, the time, and the position. So these are all the features we have. And with that, we obtain an F1 of 0.65. Then we add the domain knowledge of, well, maybe when they were close to a city, they stopped there to get some food from the city, or they try to avoid it and they keep moving. Yes. So we use geonames.org for Nigeria and Cameroon, and that has several thousand cities for each of these countries. And then we use GeoPy distance, and we filter only the cities that are less than 50 kilometers away from, and sorry, I would like to increase the font, less than 50 kilometers away from the center of the points. And we get these cities, yeah? 7 cities. So we add now to the data 7 more. But these cities are not that good, this one in brown, because most of the points are concentrated here. We're going to get these 7 cities here, but nothing around here nor around here. Yeah? So with these 7 cities, the system produces a little better results. Yeah? So what I would like is for you to later on your own time, take this data and do some clustering. So you can find landmarks through clustering. Yeah. And if you're not inclined or you run into some problems, I have that in the file called Spatial Landmark from Workshop. You do have, and this data is actually very nice. The clustering works really well. Yeah. So that's all for these. But the other thing that can be done here, which is much more advanced, is in the data set you have there from Cameroon and Nigeria, you have the elevations of all these cities. So you can run a ordinary kriging, like, and obtain an interpolated elevation for each of these birds' positions. Yeah. the data set contains the elevation. So from the data set, but you don't know the elevation of the terrain. You know the elevation of the GPS marker, and it's a bird, so it may be on flight. Of course, if you have the elevation of the terrain and the elevation of the bird, you will definitely know whether it's on flight or not. So that's it for this example. But as you can see, this is a relatively simple technique and can be very useful. And also landmarks are very much the way we humans think about locations. Yes, we don't think about this GPS. We think about you are close to, you know, this neighborhood, or you are close to the city center, or you are close to this mountain, correct? Okay, so now for the time series. So this data set and problem, I think is very useful for the work you have done collectively for tracking COVID in Nepal. You can try to use some of these models to predict bedrooms, ICUs utilization, and things like that. So again, the idea here is we have a small data set of country-level population, yes? So the World Bank distributes for all countries in the planet yearly population since 1960. So that's the data set we'll be using here. And crossing that with the number of inlinks and outlinks on a Wikipedia page. And for that, I use DBpedia, which is a little ontology extracted from Wikipedia. So this is some processing to get the list of countries, yes. So we have 217 countries. We are going to use 173 for development. And here we get a graph that shows this is the number, the log number of relations in the Wikipedia page, and this is the population. So these are bigger cities, yes, and bigger cities have more inlinks, yeah. So you have some sort of correlation here. What it means is that, sorry, bigger countries. So the bigger the country, there are more pages in Wikipedia that link to that country, yeah? But in general, the number of outlinks that you get is fairly stable. Yes, the page itself normally references roughly the same number of items. So these are the two features we will be using to predict the population of a country. And so here's a little bit of EDA for the different countries. Take some countries at random. And you can see that most countries kind of go up. Sometimes have some years where the population grows a little more. Sometimes they, in the case of islands, for example, it grows and then it just stabilizes because you're going to fit more people in there, yeah? Or the same with small countries like Slovak Republic. You have missing data. St. Martin didn't exist as a separate country until the late 90s, yeah? And sometimes you have reversals. You have, like here in Ireland, there was a big emigration in the mid 80s, so the population actually went down, yeah? So the first approach is just no time series data. We are trying to predict a particular value using this feature, yeah, the inlinks and outlinks. And for this, I'm using support vector regression, yeah, and I'm doing a little bit of a linear search for the best parameters rather than a grid search, so it runs fairly fast. And this is what we get. So we get, for different sizes, so each of these points is a prediction, yeah? And we are trying to predict the population in 1960, 1961, 1962, but the model doesn't have any concept of time, so predict these boxes because it's giving you the same prediction for the same country for a period of time. But even though this has a big error rate, still follows the curve somehow. And that's pretty impressive. If we do some more analysis, we see the predictions, yes, are, this is what it predicted, this is the difference, and this is missing 4 million people. Yes, so the system is still quite far. And what we get is that it underpredicts Far East countries like Thailand, but overpredicts European countries like Bosnia and Herzegovina. Why? Because I'm using the English Wikipedia, and the English Wikipedia then will have a lot of links, a lot of pages for European countries, but Far East countries won't have so many links, so the model thinks they are less populated. Now, if we add time series here as a feature, what we do is we make one training instance for one particular year, say 1975, and then we take 10 years earlier the population. So the features is the number of inlinks, the number of outlinks, and the population in 1965, and so forth, so on. Yeah. So we take this sliding window and focus on the. We train from 10 years in the. We started training, so the data started in 1960. We start training from 1970 and on, because otherwise we don't have that. And we take 10 years difference because very likely this data is interpolated on itself. You only have census about 10 years in time. So that's where we started 10 years earlier. Otherwise, we will just reverse engineering whatever interpolation the World Bank did to get this data. And so with that, we get this curve. And this is a very nice curve. Yeah? When we do some analysis here, what we get is that we are still missing 3 million people on this small held out sample. Yeah? And what I encourage you to try is to start adding a longer window. Yeah? So instead of using only 1960, you also, instead of using the population 10 years ago, you use the population 10 years ago, 11 years ago, 12 years ago, and so forth, so on. That thing, you have the some solution here. It using a few years won't help you that much, but using 10 years more will definitely help you. And so far, the lowest I got was 2 million people. Yeah, of error. So, but definitely, I think you want to try here is to run the ADF statistical test that will give you the P and the Q for that window. So you say, in the last 10 years before coming to this year, how was the curve? It was going up, it was down, it was an AR1 process, it was an AR2, and then you add a feature just with those numbers, with the P and the Q. And depending on the machine learning system you're using, it may be able to profit from that information to build the whole system. If you want to see an example of that, that is in chapter 7 of my book, and you have the whole IPython notebook, and you can see there the libraries used and stuff to do those tests. They take a little bit of time to run, and they tend to complain a lot on the, give you a lot of warnings and things, because they really expect the data to be done by hand, cleaning each of the time series. So if some matrices are not well defined, it complains a lot. But well, that's what I had to share with you today. Any more questions?
Are there any more questions?
So if you were to apply this to the COVID data, yes, you can see that you can then combine the historical samplings with features you have for that particular hospital or place, for example. So I hope you would like to play with these Jupyter notebooks and try to, to learn these techniques. There is nothing that will be better than that you work on it yourself. Feature engineering is very time consuming. So it is quite hard to organize a training that will have the amount of time for you to try all these different iterations where you are training models and you are fitting parameters. But I hope you try it. And if you have any issues or questions, you can send me an email to my Fusemachines account.
I thought it was interesting what you were saying with you started off with saying how we trade off space with time and time with space, and I thought it was interesting to put that into perspective when you said, with deep learning we can put like a lot of data, which is space, and we can substitute that. If we don't have a lot of data, we can make up for that with a little bit of our time. I thought that was kind of poetic, actually.
And also it's at the end of the day, we care about solving problems. Yes.
Yes.
If you try to write a research paper or things like that, then you care about advancing science. It's a very different goal. I feel right now we are consumed in something that comes more from a scientific perspective than an engineering perspective. And that means that there are problems that we could be solving that we might not be solving because we are trying to use a technique rather than solve the problem.
Right, like the cool technique.
These things are not cool. I mean, these landmark stuff or these are very simple things, but they make a big difference when you find the good landmarks. And right, so thank you very much. Thank you for your time. I hope you have enjoyed. And in some year, I'll be in Nepal and I'll get to meet you in person.
Yeah. Well, great. Sorry, just a minute. So if you have any key takeaways, can you just jot down some key takeaways from this session?
Sure. So the main takeaways.
Like attendees.
Oh, attendees. Yep.
Yeah. So please note down some the key takeaways from this session, what you learned from this session. We'd love to see more in the chat. Or if you don't want to say chat, you can just say it, unmute yourself and just speak up.
Hi, Paul. So yeah, I actually had a couple of questions. One was around what's your usual go-to method for interpretability of what the machine learned for all of the features, and the other was when we're deriving features, say doing some transformation on one feature, we're sort of introducing correlation between the features, and so how do we reconcile that with the fact that we usually don't want that much correlation between features themselves? Obviously, we need some correlation there, but essentially, how can we decouple sort of what correlation to keep and what to disregard? Is that just driven by the final metric, or?
So when you bring the issue of interpretability, yes, there are certain problems that's really important. Like if you are doing, say, credit score models, yes, you have to comply with the law. So you need to have a model that a lawyer can look and say, yes, this is legal, yeah. So in those cases, you will be renouncing to having a better quality model, to have one that has less features but are very clear and very interpretable. Yeah. But otherwise, it really depends of how much the domain experts are involved. Yes. If for you all the features are opaque and you really don't understand what they mean, then interpretability takes a back seat. Somehow, many times working with people, I see that we fail at engaging the available experts. Yes, we don't work so much on trying to ask them just which feature do you think this will help. Yeah. So in that case, if you can have an expert that will help you, most probably then you will want to have fewer features that are much more informative. And many times those features will require a whole machine learning just to compute that feature. Yeah. So like things like intention to buy, yes, or things like that are much more abstract. You can train a system just to come up with that. But yeah, this is all for the most part done in a case-by-case basis. I haven't seen any theory for that as such.
Thank you. That was Vijay.
Mm-hmm.
Are there any more questions? Like Vijay, is your query clarified?
Yeah, sure. Yeah, on the interpreted part. And Pablo, what about for the correlated features? Well, I mean, when we're deriving new features, we are sort of introducing some correlation between features.
I'm having a little hard time. So you're talking about correlated features. That's what you're saying?
Yes.
Yeah.
And and not in a way that we're just, for instance, if we have, say, the discount percent for a particular time, we might transform it in different ways. Maybe take the log, or maybe just take the actual price magnitude and so on. So we might have different features. We might take different features that are sort of indicative of the same thing. So essentially, how is there a way to sort of go about it systematically, or it's just a case of putting them in and then seeing how it...
So if you were about really systematic on that, just use AutoML, because AutoML is doing that. Yeah. AutoML is going to try everything in as much as you have computer available. Yeah. So it has this palette of operators, and it will try these different operators. The idea is that you have some reasons based on your understanding of the problem that certain feature drill down will help. Yeah. Then the big question about whether after you do the feature drill down, you will have the operated feature side by side or replace. Yeah. And to me, that really depends on the machine learning system. There are machine learning systems that are going to be very unhappy with highly correlated features. Yeah. While others will be just perfectly fine with them. But my preference in general is to replace it first. Yeah, so I just replace, and if it helps, I keep doing drill down. Yeah, and in a way, you want to find when the drill downs don't help anymore, and then start backing up from there to improve your understanding of the problem and how the machine learning is reacting to your actions. But it's slow, depending on how long it takes to train the model. I don't know if this helps. You can do many of these things with a grid search from scikit-learn.
Yeah, makes sense.
But one of the big problems with feature engineering is that there is not that many clear-cut answers. And that's something that I mean, I wrote the book based on material that I researched for, yes. And many times there were questions that I wanted to answer, and there was no answer available. Yes, so as we progress in our understanding of machine learning, of problems, we can answer more things, but there are some clear-cut questions that don't have a clear-cut answer yet. What we know is there is something called the no free lunch theorem for optimization that says that there is no machine learning system that will work for all problems. Yeah, so that's a mathematical result. And if you can do the feature engineering automatically, well, that's another machine learning method. Yeah, you have the machine learning plus the automatic feature engineering. That thing is a machine learning. So overall, there will be more continuous need for human intuition and from my perspective. Always nice chatting with you, Vijay. Thanks for joining.
Yeah, thank you. Thank you for the session.
Are there any more questions?
I think I have one last one. It's slightly related. So whenever us humans, we're trying to make conclusions about something, we hear this phrase a lot that correlation is not equal to causation. But with machine learning, because it gets the job done, we kind of look for features that are correlated. Do you in the future see that changing? Because I mean, us humans are held to a different standard with correlation and causation, but with machine learning algorithms, we kind of like search for correlation, you know?
Well, but we're just predicting something. So the fact that this system predicts that using this data, hard to say. So the normal example is number of ice cream sold together with number of murders, yeah, or number of shark attacks. Well, but if you are a city and you're trying to see how many shark attacks you are going to have to prepare your IC units and schedule people, lifeguards, yes, in the beach, and you have a stream of data from how many ice creams are being sold, you know this doesn't give you causation, but it helps you predict. So why are you not going to use it? So the problem is not the causal link is important if you want to do policy or other type of things, but if you want to predict and solve things, it's fine.
Yeah, I think it's interesting, and I think that's also part of the reason why there's such a problem with interpretability, because we're just taking things that correlate, and we're taking that ice cream, and we're trying to see how that connection is, and it doesn't exist, you know. And
completely agree with you, but that's a management problem. Yes, people come looking at the machine learning model, look at the sharp scores and stuff like that, and making bizarre conclusions. I think our job as technical experts to say, no, you cannot do that. When I was in the Watson project, in some moment, somebody wanted to use the weights on the logistic regression to say which person was doing good job or bad job. And I was like, no, the weights even normalize things. So if the feature is very big, it's going to be a very small weight, but it's just because it's so, I mean, even worse than using just sharp scores, it's just the weight of the model. And that temptation is in us because we like to simplify things. Right. But yeah, so we need to be vigilant about that. But the good part is that with all these causal inference models, that the theory that came out in the last 15 years, now there is pretty good math to calculate those things for real. And that stuff, at least we can say, no, you cannot do that, but you can compute these other things.
Right. Thank you.
Thank you, Ishu. Are there any more questions?
All right. So I'll send you my regards.
By the way, Pablo, I just couldn't recognize you with the new haircut.
It was sadly with the coronavirus stuff. You need to stay clean with my hair. I don't like it to keep it so short, but we live downtown and people are not distancing very well here. So, but
You look handsome, actually.
Yeah, I've been told that it's on my contract that I have to have the hair like that. It's like, my wife is like, this is the Pablo I married, not that long hair. So it's making the wife happy. But my son misses the beard. He likes to pull it and stuff.
If wife is happy, you're happy, right?
Of course. So thank you very much, and we can see how this is received, and maybe do a second one in a few months or something so about some of the other topics. But I'm very, very happy to talk with you.
Yeah, thank you Pablo, for the insights on the feature engineering over spatial and temporal data. And thank you everyone who edited in this session, and hope it was helpful for everyone over here, and we'll share with you all the resources for this session.
Thank you very much.
Pablo, do you want the attendees to complete the complete everything that you mentioned in the notebooks?
I mean, to me, if they do the notebooks, the first part, that will really mean they have got what I wanted to share with them. Yes, otherwise these things are too abstract, yes. But it also depends on the type of customer problems they are dealing with. Stuff. It may be that they just want to keep it there and use it when they engage in a problem on that. Yeah. You learn by doing. Thank you very much.
And thank you, Ishu and Vijay, for the questions. And thank you, Mahendra, Chiti, Srikar, Prajin, Roshan, for jotting down the key takeaways from this session. We will send you all the feedback from the session, and hope we all can see you in the future sessions, and hope we can organize more sessions with you, Pablo.
Bye-bye.
And thank you, and have a great day ahead. Stay safe, stay healthy. Bye-bye.
Bye-bye.
Take care.
Bye.